Chapter 24, Beyond Our Solar System. Properties of stars. Distance. Distances to the stars is very large. Units of measurement that we use are kilometers or astronomical units, so too cumbersome to use. A light year is used most often. The distance light travels in a year, so 1 light year is 5.8 trillion miles. Other measurements of measuring distance are also used. Stellar brightness. This is controlled by 3 factors: size, temperature, and distance. The magnitude is a measure of stars' brightness. There are 2 types of measurement. Apparent magnitude is the brightness when a star is viewed from the Earth. It decreases with distance. Numbers are used to designate magnitudes. Dim stars have large numbers, and negative numbers are also used. Absolute magnitude, or true or intrinsic brightness of a star. Brightness at a standard distance of 32.6 light years. Most stars' absolute magnitudes are between -5 and +15. Interstellar matter. Between the stars is the vacuum of space. A nebula is a cloud of dust and gases. 2 major types of nebulae. A bright nebula glows if it's close to a very hot star. 2 types of bright nebulae: emission nebula and reflection nebula. A faint blue reflection nebula in the Pleiades star cluster. Dark nebula, or not close to any bright star, or paradark, contains matter that forms stars and planets. The Hertzsprung-Russell diagram, or HR diagram, shows a relationship between stellar brightness, absolute magnitude, and temperature. This diagram is made by plotting each star's luminosity, or brightness, and temperature. The main sequence of stars, several parts. The main sequence of stars is 90% of all stars. It's a band through the center of the HR diagram. The Sun is in the main sequence. Giants, or red giants, are very luminous, large, are on the upper right on the HR diagram. Giants, very large giants are also called supergiants. Only a few percentage of stars are supergiants. White dwarfs are fainter than main sequence stars, are small, approximately the size of the Earth. They have a low central area in the HR diagram. Not all are white in color. Perhaps 10% of all stars are white dwarfs. So here's our diagram. Here's our main sequence. 90% of all stars are in the main sequence. And right up here is where the Sun is, right in the middle of that. Okay? The giants are more luminous, okay, and they're going to be up on the upper right. The white dwarfs, less luminous, and they're down below. Stars, this variable stars are stars that fluctuate in brightness. Types of variable stars: pulsating variables. They fluctuate regularly in brightness, they expand and contract in size. Eruptive variables are there's an explosive event, a sudden brightening called a nova. Okay, stellar evolution. Stars exist because of gravity. 2 opposing forces in a star: gravity, which contracts matter, and thermonuclear energy wants to expand it. Stages of birth: a star in dark, cool interstellar clouds. Gravity contracts cloud and temperatures rise. Radiates long wave of red light and becomes a protostar. And a protostar, gravitational contraction of gaseous clouds continues. Core reaches 10 million degrees Kelvin. Hydrogen nuclei start to fuse, becoming helium nuclei. This process is called hydrogen burning. Energy is released. Outward pressure increases. Outward pressure is balanced by gravitation pulling in. The star becomes a stable main sequence star. Main sequence stages. Stars are at different rates. Massive stars use fuel faster and exist for only a few million years. Small stars use fuel slowly and exist for perhaps hundreds of billions of years. 90% of a star's life is in the main sequence. Red giant stage. Hydrogen burning migrates outward. Star's outer envelope expands. The surface cools. The surface becomes red. The core is collapsing as helium is converted to carbon. Eventually all nuclear fuel is used and gravity squeezes the star. Burnout and death. Final stage depends on mass possibilities. Low mass star with a half solar mass, so half the mass of the Sun. Red giant collapse becomes a white dwarf. Final stage depends on the mass as well. So now the medium mass star is going to be between 0.5 and 3 solar masses. So red giant collapses, a planetary nebula forms, and then becomes a white dwarf. Okay, so here we have an HR diagram showing stellar evolution. So we have our dust and gases that coalesce and form a protostar. Okay, when it stabilizes, it jumps into and joins the main sequence. as the star starts, depending on how massive it is, when it starts to die, it may become a red giant, and then become a variable star, and then a white dwarf, and maybe a planetary nebula, or more planetary nebula, and then a white dwarf, and then back to dwarf stage. Now, a massive star over 3 solar masses has a short lifespan, terminates in a bright explosion called supernova. The interior condenses. We may produce hot, dense objects, either a neutron star or a black hole. White dwarfs are small, some no larger than the Earth. They're dense. They can be more massive than the Sun. A spoonful weighs several tons. Atoms take up less space. Electrons displace inward, called a degenerate matter. Hot surface and cools to become a black dwarf. Neutron star forms from more massive star. Stars have more gravity, squeezes itself smaller, remnant of a supernova. Gravitational force collapses atoms. Electrons combine with protons to produce neutrons, and it's very small in size. A pea-sized sample weighs 100 million tons. Sample density as same density as an atomic nucleus. It's strong magnetic field. First one discovered in the 1970s. This neutron star. Pulsars, pulsating radio source, found in Crab Nebula, remnant of a supernova from 1054 AD. There's a Crab Nebula in the constellation of Taurus. Black hole, more dense than neutron star. Intense surface gravity lets no light escape. As matter is pulled into it, becomes very hot, emits X-rays. Likely candidate is Cygnus X1, and it has a strong X-ray source. That's black holes. Types of galaxies. Existence was first proposed in the mid-1700s by Immanuel Kant. 4 basic types of galaxies. A spiral galaxy, arms extend from nucleus. About 30% of all galaxies, large diameter up to 125,000 light years, contains both young and old stars. The Milky Way, our galaxy, is a spiral galaxy. Here's spiral galaxy Messier 83. So you see it's a central nucleus with arms rotating out. A barred spiral galaxy, stars arranged in the shape of a bar, generally quite large, about 10% of all galaxies. An elliptical galaxy, ellipsoidal shape, about 60% of all galaxies. Most are smaller than spiral galaxies, however, they are also the largest known galaxies. So here's a barred spiral, so the stars are more lined up. A regular galaxy lacks symmetry, about 10% of all galaxies contain mostly young stars. The Magellanic Clouds is an example. Galaxy clusters, sometimes galaxies are grouped together. Some contain thousands of galaxies. A local group, our own group of galaxies, has at least 28 galaxies. And superclusters, a huge swarm of galaxies, may be the largest entity in the universe. Shifts, the Doppler effect. So again, Doppler effects change in wavelength of light emitted by an object due to its motion. Movement away stretches the wavelength. So longer the wavelength, the light appears redder. Movement towards squeezes the wavelength. Shorter wavelength, light shifted towards the blue. Amount of Doppler shift indicates the rate of movement. So a large Doppler shift indicates a high velocity, small, a low velocity. Expanding universe. Most galaxies exhibit a red Doppler shift, moving away. Okay, so it's kind of like here's a raisin bread analogy of the expanding universe. So you make your bread dough, and you put some raisins on the outside of it. And then as that dough rises, okay, so it gets larger, those raisins start to spread out. Okay, so most galaxies exhibit that red Doppler shift. Far galaxies exhibit the greatest shift with the greatest speed. Discovered in 1929 by Edwin Hubble. Hubble's law. The recessional speed of galaxies is proportional to their distance. This accounts for the red shifts. Big Bang Theory accounts for other galaxies moving away from us. The universe was once confined to a ball that was supermassive, dense, and hot. Big Bang marks the inception of the universe, occurred about 15 billion years ago. All matter and space were created. Matter is moving outwards. The fate in the universe has 2 possibilities. The universe will last forever. Outward expansion will stop, and gravitational contraction will follow. Final fate depends on the average density of the universe. So if the density is more than the critical density, then the universe will contract. Current estimates point to less than critical density, and we predict that the universe is going to be ever expanding or open universe.